The purpose of this video is to go over 3 different kinds of calorimetry problems that you will encounter on ALEKS. So the first thing I want to point out about calorimetry problems is there is one and really only one equation that you're going to have to use in order to solve these problems. And that very equation is Q heat equals M mass times specific heat times the delta change in temperature, with delta change in temperature being T final minus T initial. The other thing you're going to have to recognize in any kind of calorimetry problem is that whatever heat is lost by one item is going to be the heat gained by the other item. And this all takes place in the device that you see over here on the right, so that whatever heat exchange occurs between one thing and another cannot escape from the container. The container is insulated, so it prevents any leakage, let's say, of heat from the thing that you were studying, which is the heat exchange between the iron, in this case, and the water, and any outside environment, which is very important. So what do we have in this problem specifically? We have iron. We're given its heat capacity. We know we're putting it in a calorimeter. We know that calorimeter contains 100 grams of water. And we have two different temperatures. We have the temperature for the iron, the initial temperature for the iron, and the initial temperature of the water. The iron is somewhat hot, it's 94.8 degrees centigrade, and the water is somewhat cool, 21 degrees centigrade. We know from common sense that if we drop a hot object into some cool water, the hot object will cool down and the water will heat up. Again, whatever is lost by the hot object is what is gained by the water. The other important fact is that these two objects will come to equilibrium temperature. Ultimately, the temperature of the water and the temperature of the metal will be the same. What are we being asked to do in this problem? We are being asked to calculate the mass of the iron sample. Note that mass is one of the terms in the Q equals ms delta T equation. The other thing to notice is we know how much water we have, 100 grams. We know what the initial temperature of water is, 21 degrees. We know what the final temperature of water is, 25.2 degrees centigrade. The specific heat of water is always 4.184 joules per gram degree centigrade. That's something in the beginning you might have to look up, but you're going to get to memorize that pretty quickly. So that means having the mass, the specific heat, and the delta change in temperature, we can, in fact, calculate the Q of H2O. And then we can take the negative of that number and set it equal to the Q of iron. So our first calculation is going to be to solve for the Q of water. We have 100 grams of water times 4.184 joule per gram degree centigrade times the temperature final, which is 25.2, minus the temperature initial, 21.0 degrees centigrade. I'm not going to calculate this. You can do it. It's understanding how to do this, not so much what is the answer. So then the next step is to take the negative Q of H2O. At the risk of sounding like a broken record, I'm going to remind you that whatever the heat is that is lost by the metal, iron, is equal to the heat gained of the water. So they are equal and opposite in magnitude, and therefore taking the negative of the one will give you the value for the other. Okay, so the Q of iron, we have all the information we need except for the thing that we need to solve for, which is the mass. So once we take the negative Q of H2O, we can easily solve for the mass, as you can see here. So this is your basic calorimetry problem. Nothing too complicated here, a few moving parts, but once you get the hang of this, not terribly tricky. There is a trickier version, a trickier incarnation of this problem. It is almost exactly the same in terms of the setup. So what do we have here? We have 18 grams of iron. Again, we're given the specific heat capacity. Again, we're putting it in water, which is at 75 degrees centigrade. We have 150 grams. And we know the initial temperature of the iron and the initial temperature of the water. What don't we know? What we don't know is the temperature final. But what we do know is that the temperature final is going to be the same for both iron and water, as we saw in the last problem. That being true, we can set up both equations simultaneously for the Q of iron and the Q of water, letting the Q of water be the negative of the Q of iron, and our delta T being TF minus TI. One thing I want to point out here, you can actually say negative Q of iron equals Q of H2O, or Q, or this way as I've written it, Q of iron equals negative Q H2O. It's going to work out mathematically either way. So you don't have to sweat the details too much on that one. So what do I mean by setting up both equations simultaneously? Well, over here on the left, we have what? We have the Q of the iron. And we know that it's 18 grams of is our mass, 0.449 is our specific heat. TF here is what we're going to ultimately be solving for, and T initial for iron we know is 5.5 degrees centigrade. This is going to equal the negative of the mass of water times the specific heat of water. Again, we have the temperature final and our temperature initial 75 degrees centigrade. So since the temperature final is the same, it's like solving for X. Granted, you have to do some fancy footwork in terms of multiplying and rearranging, but it is eminently possible to solve for TF. You just have to be a little careful. What's more challenging about this problem is having to set up these equations simultaneously, remembering that one is the negative of the other, remembering that they're both going to come to an equilibrium temperature, and you can represent that in your separate equations, and so forth. Once again, once you get the hang of this, not so bad, but there are more than a few moving parts. The next thing we want to consider is conducting a chemical reaction inside a calorimeter and how that allows us to determine the enthalpy of the reaction that is being conducted. In this case, a student takes 10 grams of sodium hydroxide, dissolves it in 200 grams of water, and observes the temperature change. The temperature of the water, actually better described as solution, rises from 23 degrees centigrade to 37.9 degrees centigrade over the course of 6.6 minutes. What is our chemical reaction? Our chemical reaction is NaOH dissolving or dissociating into Na plus and OH minus. This is a chemical reaction. Bonds are being broken here. So we have some data to work with. We have our 10 grams of sodium hydroxide, our 200 grams of water. That's going to give us a mass. We have a delta temperature change. And because this is a solution, we can equate its specific heat to that of water. We can say that the specific heat of this solution is 4.184 joules per gram degrees centigrade. This is going to allow us to use the equation Q equals ms delta T. But we have three questions to answer here. We have first to evaluate whether this is an exothermic reaction or an endothermic reaction or neither. Well, we can see here that the temperature has gone up. So this reaction must be releasing heat to the solution itself. You can think of the reaction taking place on this microscopic level, and actually, depending on whether it's endothermic or exothermic, either absorbing heat from the solution or releasing heat to the solution. So, answer to question number 1, based on the temperature going up, is this reaction is exothermic. Next up is calculating the amount of heat that was released or absorbed in this case. What is this case? This case is we reacted 10 grams of sodium hydroxide in 200 grams of water. What's our mass of solution? Well, if you combine 200 grams of water and 10 grams of sodium hydroxide in a beaker, you have a total mass of 210 grams. We just said we know the specific heat. We just said we can figure out the delta T. So we take 210 grams, our mass, times the specific heat, 4.184, times the delta change in temperature, and we get a number, 13,091.7 joules, which we convert with the appropriate number of significant figures to 13.1 kilojoules. This gives us our answer to part 2 here, the second question. Calculate the amount of heat that was released or absorbed by the reaction. In this case, that's going to be 13.1 kilojoules. Now, this is the amount of heat that is released based on reacting 10 grams of NaOH. However, in the third question, we're being asked, what is the reaction enthalpy per mole of NaOH? Well, 10 grams of NaOH is not a mole. In fact, if we do the math, we find out that it is 0.25 moles of NaOH, and that's where you have the situation where you generate 13.1 kilojoules of heat. So, in order to get at the per molar basis, all you have to do is take the 13.1 kilojoules of heat, divide by the 0.25 moles of NaOH, and this will give you the per mole basis. 52.4 kilojoules per mole of NaOH. But now we need a negative sign. Here we didn't assign negative or positive. Why? Because it is the convention when you say released or absorbed not to use a sign. We think of it as just an absolute quantity, and we just put the number in there. However, the minute you see delta H of reaction, this needs a sign, because this not only tells us the heat transferred during the reaction of this 1 mole of NaOH, it also must specify whether it's exothermic or endothermic. And in this case, since it's exothermic, we need the negative 52.4 kilojoules. So that should give you the tools that you need to tackle these 3 different ALEKS problems, and generally give you the principles of calorimetry and how to use the appropriate equation and calculations.